Machine learning. Great to see everybody. How many of you tried machine learning? How many of you liked machine learning? All right, so first thing first, let me tell you about this guy, Dominic. He was supposed to be here with me, but unfortunately he couldn't come. But that's okay because he worked on this project with me, and now I'm going to show you what we did together. We met last year in Angular Connect, where we watched a talk from this awesome guy called Asim. Now, Asim was showing some cool stuff with machine learning, like this demo where you use Azure Cloud Services to detect the emotion that you had on his face or any picture that you gave it, and to emojify it. And he also spoke about a vague concept. He didn't really show a demo because he didn't have a demo, but what if we could just like type a couple of words inside a text field and hit submit, and that would generate an app for us, like just by typing what we want to have on the screen. And that inspired Dominic and me to think, wow, how can we actually build that? So thank you, Asim, for inspiring us. Thank you. Yeah, I will send him the video later so you can hear claps. And we started brainstorming. But before I will tell you about the brainstorming of that, I'm a little bit cold. So I'm going to start training my machine learning model right now, which is going to hit the CPU, and I will get some heat from the computer. And then we had a bunch of ideas like what he showed, and we started to narrow it down. Like he had this crazy idea where we just sketch an app on a paper, scan it with a phone, and the machine learning would generate the app from the sketch. Didn't happen. But eventually we narrowed it down to a research question. We said, if we have a function signature like add that gets x and y, we want the machine to write this code for us. Now, obviously, this is a hard task even for a human being. Imagine if I give you a function called size of shoe that gets name string. How would you implement that? No, that's racist. Anyway, so before we get into the machine learning, the actual research question, a few words about like machine learning in general, how it works. So machine learning 101, while my algorithm started running. Basically, machine learning, like self-driving cars and all of that, you know, it's used in many places. Even this is actually a cool example. This is a data center where they use machine learning to control the cooling. So they know how to make the fans cool it the most efficient way and save power for our plant. But Tachlis, machine learning, this is a standard program for classifying spam messages. You know, just by looking at a subject, we can write a bunch of rules like if the email contains the word millionaire, it's probably a spam, right? And so on. But with machine learning, we don't actually have to write all these rules. Machine learning is all about giving it just a bunch of examples and telling it, this is spam, this is not spam, and then running some kind of classify magic that would eventually learn how to predict, given a subject, whether it's spam or not. So traditional programming is just writing all the logic and to every single write down every single detail, while machine learning is just, you know, you give it the samples and magic happens. Not really, it doesn't happen. I will show you. So one of the algorithms, there are plenty of algorithms like random forests. I don't want to get lost in the random forest. But one of the algorithms, neural networks. Have you heard about artificial neural networks? So yeah, inspired by what we think we have in our brain, I mean in your brain, mine has nothing. So neural networks are basically just numbers. So this is what we call neuron in artificial neural networks, which is basically a function that takes a few numbers, in this example 2 numbers, it does some calculations and returns a result. So basically, it's a function that takes some numbers, does multiplication and additions, and returns numbers. Now, the important thing to remember here is that you feed it numbers and you get numbers. And we want to work with that text, which is a challenge. So we'll get back to that. And this is simple. I mean, you can implement it. It's like one line of code. It's like x times 0.2 plus y times whatever, and you get a result. And this is like the model. But how do you train? How do you figure out those numbers you need to multiply by? So we use another algorithm that basically gives it some input, looks at the output, it knows what the right output should be. In this example, it should be 15 for some reason. And then it calculates the difference, the error, and it updates the numbers to make the result close to what we want it to be. So basically, machine learning is just adding multiplying numbers, and training machine learning is just running this calculation, looking what we got, and tuning the numbers until everything is starting to look right, like your accountant does for a living. And this is simple, but real machine learning code is a lot of this. Like we have like 6. In real machine learning, it's thousands or 10 of thousands. And this is like a quick introduction to neural networks, but this is not the most challenging part of this project, because as I told you, this is a solved problem. Like you have these algorithms and you can use them and they work with numbers, but we want to predict function bodies, which are text. So let's look at a function like this function greet. If you wanted to predict the body for that function, first of all, we would do this process iteratively. Like we want to have a model that will get the name of the function, in this case, the signature, and it will return the first word, the first character in this function, which is the opening curly brace, and then we will iteratively call the model and get the next part each time. So basically, we want to, instead of like giving this block of text, return us this block of text, we are giving it the beginning, and then it gives us the next part each time, step by step. So that's like what we are going to do. And in order to do that, we need to get a lot of data. And after we get the data, we need to clean it, which we are going to spend a couple of minutes doing right now. And then once we have all the data ready and cleaned for the model, clean means numbers, not text, we just choose a model. Or I will tell you a secret. We copy a model from somebody who. And then we train it. I mean, we are training it. As you can see, it takes a long, long time, but it's warming my hands, so I'm happy. And eventually, we get some model, and we start to evaluate, and it doesn't do what we want it to, but it's still funny, so that's cool. So that's the high level of every machine learning problem that you are going to tackle. You are going to go through these first 5 steps, and then go back and restart until you are satisfied, or forever. And oh, the most important step, make money, of course, once it eventually works. How do you think we can get a lot of examples, like for functions, for training this model? Where can we find many functions? Open source code on GitHub, right? Applause to you. You know it, you know. But you know, how would you download all the code from GitHub? CURL. Okay, so you go to the other room, download with CURL. I will show you a better method, but thank you for being brave to say that. So CURL is the slow way to download repo by repo. Fortunately, there is a product from Google, Gold. It's also gold. This is how I mined Bitcoin on Google. It's called BigQuery. Anybody heard of it? Everybody? Wow, cool. So BigQuery basically lets us run SQL queries really fast on a large amount of data, and they have the entire GitHub code in BigQuery. So basically, I used BigQuery. This is BigQuery, by the way. You see, I ran a SQL query on all GitHub, And you can see it even supports running JavaScript code, calling JavaScript functions from the SQL query. So basically, I'm using some library from a guy called Craig. Craig, are you here? He's here in the conference. He spoke this morning. And it allows me to run queries on TypeScript code using the abstract syntax tree. We'll talk about the abstract syntax tree later. But basically, I can run this function I wrote in JavaScript on all source code on GitHub and quickly get the results. So as soon as I hit run, you can see it's now running this code on like millions of files, of TypeScript files on GitHub. And in a few seconds, I'm going to have all the functions that exist on GitHub inside TypeScript files. Usually that takes around 40 seconds. So let's count down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now I said usually, sometimes it takes longer, so we don't know. But you know, it has to go over 2.2 gigabytes on data and run this processing over there. And as soon as we have the results, you will be able to see it. Oh, we got it. We got it, yes. Let's make the font a little bit smaller so we can see more. And you can see like we have, you can't see because the font is still too big. Hide editor, yeah. We basically have the path to the file, the hash, and the actual function. So at that stage, we already have like a lot of data we can test with, a lot of functions we extracted from GitHub. And first thing solved, we gather the data. Eventually, we have like, actually, we have a little bit more now. We have 388,000. It used to be 324. So thank you, developers, for creating more examples for my model. Finally, we got a lot of data. This is a function, you know, and the first thing we want to do with this function is split it. So we split the signature, which is what we give to the model, from the body, which is what we want the model to predict. After we did that, so the thing is, I want to teach the model TypeScript. I don't want to teach the model English. So I'm going to take all the English out of this code, or more specifically, I'm going to take out the variable names and the strings and just replace them with placeholders. So basically, what I'm left with is sort of more abstract version of the function. It still works the same, except all of the strings are replaced with placeholders, and all of the argument names and identifiers are also replaced with the placeholders. And the reason I do that is because I want to make the job of the model easier. I don't want it to have to learn how to name variables, because you know that's hard, really hard. Just the structure, just like generate the structure of the code without naming variables and coming up with strings and Unicodes and unicorns and emoji. Anyway, so for that, I can actually show you some of that with live coding and TDD. Do you want it or do you really want it? Who wants it? Who really wants it? Okay, so let's go to the Visual Studio Code. And unlike Nir Kaufman, I'm not going to give away any free licenses. And I wrote a test. This is just like the part of, I called it generified string, just the part that takes a function and replaces all the strings with placeholders. And again, the idea is that if we look across the entire data set of the functions, after these transformations, all the strings will be quote 1, quote 2, so the model will see quote 1, and they will know, okay, this is like the first string that appears in the code, and it doesn't matter like what the value is. So this is TDD. This is like the input, and this is the output. I want it to change all the strings to numbers, and if a string repeats more than one time, to use the same number. So in this case, hello will be 1, world 2, and robot is 3. And since I really love TDD, I'm going to show you a tool I use all the time called Wallaby.js. Any users? No? Okay, this will change after the talk. By the way, it costs money. I will start Wallaby, and Wallaby is basically running my tests as I write the code. So as soon as it starts, it might be a little slow because I'm also training on this machine. As soon as Wallaby starts, I will see it will run this test and all the other tests I have in this project, and I will see that this test is not running, it's not doing anything, it's failing because my function doesn't do anything, right? So I think I will kill the training because that kills my machine. And it's not gonna finish anyway. Oh, yes. I can hear the fans. And you can see, so right now this is fails, and Wallaby shows me that it fails because it expects the value to be something, and basically the function currently returns nothing, undefined. And now I'm going to create a small source code transformation with that tool I call it, tsquery, that will replace the string. Let's see how we do this. So the first thing we want to do, we want to take the source code. So this function in the test, it receives the source code. You can see Wallaby will print, this is what we get as an input. And we want to take it and change it into AST, which is the representation of source code we can work with easily. So let's import tsquery. So I turn it into AST, and then I can use this tool called tsquery, which allows me to select parts from the code using something that looks like CSS selectors. So I'm going to take all the strings by calling tsquery.query. I'm going to query the abstract syntax tree, this AST, for all the string literals, and I want you to return the type of string literals and string literal. You see, that's what I love about Wallaby. I get runtime errors as I write a code. It's a runtime error. It's not like compiler error. And then let's see how many strings it found. It found 4 strings because I had 4 strings in the input, so it makes sense so far. And now what I want to do is replace each string with a number. So I'm going to iterate over them. So for let s of, actually let's use const s of strings. Let's start by logging the value of the string just to see that it found the right string. So it found 4 strings, hello world, hello robot. And basically all we have to do now is just to ask the AST, where are these strings in the source code in that string we got, and replace them with numbers, which can be easily done. I will use an helper array. I actually created a small interface that will help us. So that will be an array of edit entries, where edit entries simply says which text we are going to replace with which. So in this case, we are going to do edits.push and say at the start of the string, like where this string starts, replace it with, go from the start of the string to the end of the string, and replace it with, like, let's start with just replacing with quote 1. All right. So basically, let me print the value of edit so you can see what it looks like after the loop. Edits. All right, so basically edits is now just an array, says at index, between index 56 and 63 in the source code, just replace it with this new text. And I have a function called applyEdit that takes the source code and the edits, and it applies the edits. So let's console log that as well. And basically, we can see that using this AST, we replaced all the string with this placeholder 1. It's almost there. We want the numbers to be different for different strings. So let's create a counter that will start with 1, and then we can use, instead of 1, counter plus plus. Yep. And we can see now that this console log prints 1, 2, 3, 4, which is almost what we want, right? We have the word hello, it appears twice, so we want to use the same number. So I'm going to use another helper dictionary. Let's call it helper dict, which will use the string as the keys, and it will just store the number we used for each string we found. And then I can say, if this, let's call it value, the text, if this value is not in our helper dict, simply add it to the helper dict and set it to the counter plus plus. And then all I have to do, we can just copy this. All I have to do, instead of using counter here, I'm going to use helper dict value. So basically, as soon as I type in this helper dict value, I expect the test to pass. See, all green? That's TDD. And that was like in 5 minutes how we created all the source code transformation using AST. If you want, you can check my AngularUP talk from last year where I elaborated more about TS-query and the AST, so you can get a better idea. But this piece of code is basically what we did for all those transformation. So changing context, back to the machine learning. So we had these replacements. The last thing we did with the AST was just adding spaces before each token, so the model can tell that grid and open parentheses are different things. We have a lot of knowledge about this because we know this is TypeScript code, and we can help the model by putting spaces between each of the tokens. And it's super easy to do with the AST. You can check the code later. It's like about the same size of the code that we wrote here. We also added the start and end symbols to tell the model where the code starts and where it ends. Not really important. The important part, though, we are still working with strings, right? How do we convert these to numbers? Any ideas? No ideas? So, with ice? Hash, okay, hash, yeah. Okay, so yeah, we built some kind of, before that, before we convert them to numbers, let's just look at what we are going to feed our model with. We are going to prepare the samples for the model. So basically, we'll just prepare a bunch of input, which is the signature of the function and what we got so far, and the output should be the next token. So basically, we are going to prepare, for each function, we are going to prepare a bunch of samples, where each sample is the signature, the beginning of the function until some point, and the output would be the next token. So that's what we are showing to the model as samples. That's what the model should learn to do. Given signature and some part of the function, it should give us the next part, the next token. And yeah, you said hash, so we create a very large hash table dictionary that maps each of the words or tokens we have across our entire data set, our entire like 300,000 functions, to a unique number. And basically, we can use that dictionary then to convert all our source code into arrays, sequence of number. So basically, function is 1, and it will be 1 across all the data set. We also need to add some embedding, so all the examples are in the same length. That makes training much easier since we deal with fixed size of arrays. And here we have a problem. Can you see what the problem is? Like, we arbitrarily said that function is 1 and grid is 2. But we might not think about that, but in the eyes of the model, that implies a relationship. Because the models, they don't work with integers, they work with floating point numbers. So the model thinks that the fact that grid equals 2, it might have some meaning. It's bigger than 1, than function. And the model eventually will return probabilities. So what do we do if it returns 1.5? Like the next token would be 1.5. What does it even mean? Like it's between function and grid? Like, anyway, so since these numbers are arbitrary and we don't want the model to like use the values to think these values mean anything, we are going to do a little trick called Hot Encoding. And it's really simple. Basically, it means instead of writing the number 2 or 5 or 6, we'll just give it another array. And that array will be all zeros except for the position that represents that token. So for example, string was 6, right? So we give it an array of all zeros, but 1 just in the 6th position. And then if we get a result later from the model, and we have here like 0.6 and here 0.4, we know that the model thinks that the next token should be a string with this probability, 0.6, and whatever 7 was with 0.4 probability. So that's a trick very useful in machine learning called Hot Encoding. And now we are finally able to choose the model. And for choosing the model, data scientists are very much like programmers. They go to Stack Overflow and they copy. So in this case, we are going to do the same, but we are going to use a library. So this problem is really similar to machine translation, like translating text. They both work with text. They both have to sort of get some input, in this case, the function signature or the source language, and generate some output, and they generate it token by token. So we are going to get inspiration from machine translation models, and we are going to use a library called Tensorflow. Have you heard about it? Yeah, the first time I hear excitement about something that is not JavaScript specific. Cool. So yeah, so we are going to do this, and we can use TensorFlow from JavaScript, but it's easier to use it from Python. And we are going to use, so TensorFlow basically includes a bunch of functions we can use. And we are using some architecture called encoder-decoder that use a bunch of this function. And again, you don't have to know what each of those does. You just copy it and start fiddling with it until it doesn't work. If you notice, there are some words like embedding, LSTM, batch normalization, and writing the code that implements that is even simpler than this graph. Let me show you. So basically, this is the same graph in Python. Yay, Python. They also have decorators. So yeah, so basically, it just, as you can see, calling functions with the same names as the building blocks and random numbers. You later feel sorry you just didn't copy and you chose randomly. And then, after we have this, we go to training. And I think you have seen on my computer, I started training, and I stopped after like 20 minutes, and it still had 31 minutes remaining. But that was only one round out of 300. So that would take about a week or so to train this model, and I only used a dataset of 5,000 functions, like a smaller one, just for test. Luckily, I don't have to do it on my laptop. I can do it on an environment called Google Collaboratory, which is like StackBlitz for machine learning. It's everything in the cloud. You don't have to install Python or TensorFlow, nothing. Just write your code and it runs. And if you look here, you can see it's a little bit faster. It's like about 6 or 7 minutes per one round, which still means I have to wait a day. But hey, this is free and it's faster. But there is even more to it. Google has released a new piece of technology called TPU, which is TensorFlow Processing Unit, which is dedicated hardware that can run machine learning. So we try to run the same code on the TPU. Basically, you can see this if statement here somewhere. Yes, this is all like the code we had to add to make this run on the TPU, and a bunch of like configuration inside the Colab. And in the TPU, it runs a little bit faster, 8 seconds per one cycle. We managed to train this model in just an hour on the TPU. So now that you know how hard it is to train, let's see how it performs. So usually for evaluation, there is like a bunch of numbers we look at. We give the model some data it hasn't seen yet. We call this the test set and see how well it performs on that. But wouldn't it be more fun just to try and see what we get? Demo time. Prepare to be surprised. I don't know what it's going to return, so let's see. So this is a small non-Angular vanilla JS. Yes, vanilla rocks. I'm going to get kicked from this conference after. Vanilla JS app that basically it takes the signature, it does all the transformation I told you about in JavaScript, and then it sends it to Python through a socket and gets the result from the model that runs inside Python. So let's start with a simple example, adding two numbers. What do you think the implementation would be like? A cat. All right, that's creative. Let's see who is more creative. I think this is more creative, right? I mean, 308 magic numbers. Let's try another one. Let's try a function that works with arrays. And good name for such function? Oh? Map? Okay, map is good. And it will take an array of numbers and a function. You know what? Let's make it even more. A function that returns a number. Okay, and let's see what the model will come up with. Is this going to be a cat or a catastrophe? So you see, machine learning is even slow. Oh, wow, 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 wow. Well, you couldn't technically say it's not correct. I mean, you don't know what well-known does. So yeah, so everything is like we put it on GitHub, and as you can see, it's still experimental. It does sometimes come up with code that is syntactically valid, and sometimes it doesn't, and sometimes it's funny, which is the most important for me. So I hope you had a glimpse into what a real machine learning process looks like and what real-life problems in machine learning looks like. And I want you to take away a few things. First of all, you have seen my laptop, the cloud GPU and the TPU. Use the cloud, it's much faster. Second thing, copy solutions from others like we do in programming, Stack Overflow. And the third thing, we spend most of the time working on these AST transforms and making this source code very easy for the model to process. So when you come to work on a problem with machine learning like this, you have to use your knowledge about the problem. And if in this case, it's a programming problem, so programmers are the best people to clean the data and prepare it, and that's you. So we are going to continue working on it, and we are going to try to come up with a better model that will save your time by writing comments for your code. That's our next experiment. Feel free to follow us. This is my blog. You can check it out. This is the source code, and I publish the slides on Twitter. Thank you.